In this lesson we're going to discuss encoders, decoders, multiplexers, and comparators. First thing we're going to do is define what an encoder and a decoder is, and we're going to determine different outputs of various ICs, and we're also going to look at gray code and what gray code involves. An encoder basically converts a decimal number over to a code, such as binary BCD. Of course, we can't really put a decimal number, but we can tie in, let's say, 0 to 9 inputs, 0, 1, 2, 3, 4, 5, 7, 8, 9, and tie those to something and have those input as the decimal number, and then that will put out the binary code. So when we put in the number 9, we get out the binary number for 9, or the BCD code for 9, which is the same thing. A decoder actually goes the other way. It converts a binary number over to a decimal number. And we'll look at some examples of these as we go on. We're also going to look at comparators, which compare two binary numbers together. They look at the two and tells you whether they're greater than, equal to, or less than the other number. So we'll do that one first. So this is the 7485. It could be a 74LS85. But basically what you have, if you look over here, we've got two different sets of inputs for our numbers. We're going to compare these two numbers. You've got A, 0, 1, 2, and 3, and you got B, 0, 1, 2, and 3. These are binary numbers, just they're weighted as 1, 2, 4, and 8, just like in binary. Just like that. These, the inputs for A is less than B, A is equal to B, A is greater than B, those are for if we want to tie another chip into it. And I'll kind of show you that when we get done going through actually how the chip works. Then you have these outputs, A is less than B, A equals B, and A is greater than B. And if you remember from grade school, the alligator eats the biggest one, right? So in this case, B would be larger. In this case, A would be larger. So remember that. Some people forget that. Let's just write this up here so we'll remember what these numbers represent. And that's just a binary representation of those numbers. And we're going to compare these two. So if you look at these numbers, A, and I just gave you these inputs, they're just random numbers, they don't mean anything, they're just random. Look at this number for A, we've got 0, 0, 0, 0. Well, to me, in binary, that's all zeros, so it's a 0. This one is 0, 0, 0, so that's also a 0. If you look at the numbers, they're equal to each other. So what we do is we put a high, and A is equal to B, and the other two are disabled, or lows. Now let's look at this one. This one is 8 plus 2. Right, because we got highs there. So 8 plus 2 is a 10. And this one is 8 plus 4 plus 1. So it's 13. Which one's bigger? Well, B is bigger. And remember, the mouth eats the biggest one, so it would be A is less than B. So put a 1 in that box and a 0 on the other two. For this one, we've got 2 and 1, which is 3. And this one we have 8 plus 2 plus 1. It's 11. And again, B is greater than, or A is less than B. So 1 there and 2 zeros there. For this one, we've got an 8. And for this one, we have an 8. So they're equal to each other. So you 1 on the equal, low on the other two. This one, we have 8 plus 4 plus 2 plus 1, which is 15. And this one, we have 8 plus 4 plus 2 is 14. Well, in this case, A is larger than B. So A is greater than B. Put a 1 there and a low in the other two. So we're just looking at numerically which one is either greater than or equal to the other one. That's all we're doing. Now, like I said, these inputs are for if you want to tie in another chip. Let's say we have another one of these comparators and we have our 3 outputs. Well, those 3 outputs are going to tie up to these. And then we've got 4 more inputs, and then we have another set of these inputs for here, for cascading them. So this would be our A's and these would be our B's. The deal with this is if we wanted to compare an 8-bit number, what if we wanted to compare an 8-bit number to together instead of just 2 4-bit numbers, we want an 8-bit number. Well, the reason we do this, we can cascade them. If you think of just a regular decimal number, and we've got, let's say we have 85 and 32. Well, if you look at that, which one's bigger? Well, 85 is bigger. What did you look at to see if 85 was bigger? Well, you looked at the 8. The 8 was bigger than 3. You automatically knew that this was greater than that one. We didn't even have to look at the next number. So what happens with this one is if A was greater than B, In this case, it would put a high out on this A is greater than B input, and this would automatically put a high out on this output of A is greater than B. We wouldn't even have to go to the time to look at these numbers inside. So it speeds up the process. It skips a step. If we were to have 35 and 31, well, in that case we got 3 and 3, which are equal to each other, so then we have to look down at these to see which one's the greater than number. So when we know 5 is greater than 1, so we have to compare the second set. So in this case, if A was equal to B on our top 4, upper 4 bits, we would put a high out on the A is equal to B, and that tells this chip, okay, we need to compare these lower 4 bits as well, and then it'll put out an accurate output here. It's a way to cascade for bigger numbers, and you can go as big as you need to. As big as the number you need to compare, you can keep going. Okay. This next one is actually an encoder, and an encoder, remember, converts a decimal number over to a binary number or some other number. In this case, it is a BCD number. This is a 74147. The N is some kind of designation for the chip, but we don't need to worry about the N. But it's a 147 chip. Again, it could be 74LS147, could be 74 just 147 by itself. There's a CMOS version of this. That's the number we're going to look at for this chip. And what we have here is we've got 1 through 9 going on the inputs, but you'll notice something. They're all have bubbles underneath them. All the bubbles going on the input. What bubbles mean an inversion of some kind. There's an inverter there. So basically what we're doing is we're saying that these are active low inputs. In other words, it takes a low to activate those inputs. Same thing for the output. The output's actually inverted when you do your binary number. So the binary number is 1, 2, 4, and 8, just like we have been doing. It's just a binary number. So what we do with this thing is we look for the lows coming in. So the low here is on a 5. So we need to do a binary 5. Well, if you think about a binary 5, what is that? Well, binary 5 is 4 plus 1, so that would actually be a 0, 1, 0, 1 in binary. Well, since it's got active low outputs, these bubbles on the output right here, we actually need to invert that when we actually write it in the boxes. Actually, the actual output for the chip is actually an inverted 5, not just 5 itself. Like for instance, this is an 8. An 8 in binary is 1, 0, 0, 0. So we need to invert that to 0, 1, 1, 1. And one of the reasons we do that is zeros carry more current with them. So there may be a reason where you need to put more current on there to drive chips. This one, you notice we have 2 of them that are low. This particular chip, the 147 chip, actually is a priority encoder. So it will always, even if you have multiple inputs tied low, it'll always pick the highest one. So in this case, it's a 6. So a 6 is 4 plus 2. So it's 0, 1, 1, 0. Invert that. It's 1, 0, 0, 1. I'm going to give you a second and let you finish the last ones up yourself. And you can pause the video, and then I'll finish them up here in just a second. Okay, let's show you, see how you did. Let's see, this one's a 4. So a 4 is 0, 1, 0, 0. So it would be 1, 0, 1, 1. This one, since there's 2 of them, the highest one is the 9. It's going to be 1, 0, 0, 1, which is 0, 1, 1, 0. And this one is a 7, so it's 0, 1, 1, 1, which is a 1, 0, 0, 0. So hopefully you got those. Pretty straightforward. Haven't gotten over the top complicated just yet, but we'll go on to the next one. Okay, this one is an encoder, or a decoder, I'm sorry, and it actually decodes a binary number, which in this case is an octal number, over to a decimal number. So you see again, we have our inputs A0, 1, and 2. Those are our binary inputs, 1, 2, and 4. These are enable lines, and basically what we have to do with enable is we have to meet these criteria. We have to have a low going here, a low here since they're bubbles, and a high here. So we need a 0, 0, and a 1 for that thing to be enabled. If it's not enabled, we put no output. In other words, they're all zeros, or all highs on the output. We have active low outputs, so whatever number we're putting in, we're actually going to put that out as a high. So let's look at the first example just so we can make sure we're seeing it okay. First thing we want to check is make sure it's enabled. So we've got a 0, 0, 1, so that's good. We're going to check those. And the binary number we're putting in is 4 plus 1, so that's a 5. Okay, 5. So we're going to look over here at the 5, and we're going to put a 0 for the 5 and a high on the rest of these. Okay, so find your number, put a low where it's supposed to go. Next one, 0, 0, 1, so that's a check, we're enabled, and we've got a 4. So put a low on the 4, put a high on the rest of them. 0, 0, 1, so that's a check. We've got a 7, so we're going to put 0 there, and highs on the rest of them. 0, 0, 1, so that's a check, and that's a 2. So put a 0 on 2, high on the rest of these. Now this one is not enabled. We don't have a low there. It should be a low. So instead of actually putting out a 6, we're actually going to put all highs. In other words, we're not going to activate any of the outputs. This one, well, we're not activated there, so again, all highs. And this one's not activated there, so it's all highs. So instead of putting out what we would have done at 3 in this case, it's all going to be highs because we're not turning on any of the outputs. So let's go on to the next one. This is what's called a multiplexer. And what a multiplexer does is it ties multiple inputs to one single output. So it's a way for us to tie all 7 of these inputs over to, or 8 inputs over to a single output. And the Y naught is just the inverse of Y. So we can do 0 through 7. We've got different inputs here, and you can see on my chart up here, I've just given you a random highs and lows. These didn't come from anywhere, they're just made up. And we have our selection line, the S1, 2, and 3 is selection for which particular input we're selecting. So again, it's a binary number. We're going to pick, like this is 0, we're going to tie whatever's on the input 0 over to our output to Y. And then we also have to look to make sure it's enabled. So the enable we're looking for, since this is a bubble, we're looking for a low. So the enable here is low. This one I just set it up as a counter. So basically in this one we're just going to count across, but I want to show you kind of how we select our lines. So we got all zeros going in, so that means we're going to select input 0. Input 0 is a high, so the output is going to be a high. Y naught is just going to be the inverse or low. This one is a 1. So we're going to select input 1. We got a high there, so we're going to high on the output, invert to a low. This one is a binary 2. So binary 2 is a 0. So we put a 0 there, 1 there. Let's go down to this one. What would this one be? Well, this one's a 5. So we're going to select input 5. Put a 1 there. Just wanted to show you that we're not just going in a row. We're only going in a row because I counted up here. This one's a 3. So it's a 1, inverts to a 0. This one's a 4, so it's a 0, inverse is a 1. We're still enabled over here. 6 is a 0, inverts to a 1. Now we've got this problem right here. We're not enabled, right? Doesn't matter that we're putting the 7 in, which would have selected line 7 input, but we're disabled. So what this is going to do is be a high Z. And if you remember from back in your devices days, high Z is really high impedance, multiple mega ohms of resistance basically. So it's basically floating. It's just disconnected the wire. It's kind of like if you had a switch tied to the signal, we just opened that switch. So the signal is not going out on Y. Y naught is also not connected to anything, so it's just floating there. The high Z though will give you some resistance there to where it will short out some of the noise and stuff. So it's really not completely open, which is susceptible to noise, but it's a really high impedance, which it will get rid of some of that noise too. So multiplexers are really neat because you can, instead of having to send over 8 different wires from one location to the other, let's say you're going from room to room, you're sending out different signals from sensors or whatever, you can get by with a single wire, a ground wire, and you really don't even need the clocks. You might have a clear line and a clock line maybe to send over. So you could get by with 3 or 4 wires instead of 8 wires. So It's a little bit easier, cheaper to send the cable out that way than it would be to send out 8 different wires with grounds for each one of them. So it would be a lot different. Okay, moving on. How about gray code a little bit? And if you remember from the lessons, we talked about gray code before, but I wanted to show you just real quick. Gray code is really used for motor shaft placement, and it tells you where at on that shaft that motor is. So it's really used more for robotics, and you really don't even see it that much anymore in robotics, for that matter. There's the difference, the comparison between the two, and like I said, you should have seen this already. We can do a gray code converter from binary to gray code using exclusive OR gates, and this is one of the circuits you could use to make a gray code if you wanted to. So we kind of talked about the encoders and decoders, looked at the outputs in the gray code. This is the end of this lesson.